Graben. The two projects I mentioned are Sulz and Landau. Sulz and Regenshofen here are in France, and the other three here are in Germany. So these are ones that you see here. Landau, Sulz, and Insheim produce electricity, and Regenshofen actually produces hot water and steam to an industrial plant, which is about 20 kilometers away. So this is Regenshofen, and this is Sulz. This is the power plant in Sulz, and you can see the actual small village of Sulz, about 1 kilometer away. Okay, now we have had EGS projects in the United States as well. In fact, the whole concept of EGS was invented back in the 1970s by the Los Alamos National Lab in New Mexico. And they had a very famous project in a place called Fenton Hill, not far from Los Alamos Lab, which was the first EGS project in the world in 1975. So you can see there's been a number of experiments over the years, but up here on the top of the list, 1, 2, and 3 are EGS projects that are actually active right now in the United States. Forge is kind of a research project, but Cape and Blue Mountain are commercial projects. And Blue Mountain in particular is currently in operation at 3.4 megawatts, and they are producing 63 kilograms per second. Blue Mountain and Cape, Utah are developed by a company called Fervo, I'll talk about in a minute. So I want to show you this picture. This is our geothermal group at Stanford. This picture was actually taken in 2016, but I want to draw your attention to this man in the middle, Jack Norbeck, who was a PhD student, graduated in 2016. So this is Jack Norbeck today here on the left. And he, together with another Stanford student, Tim Latimer, actually founded the company Fervo Energy in 2017. And they took on the task of developing EGS commercially in the United States. And Fervo has done some very different things than what everybody else did previously in places like Sulz and Regenshofen. So Fervo decided to actually capitalize on the application of oil and gas technology from shale oil and shale gas and drill horizontal wells in geothermal, which had not been done before, and to do multi-stage fracturing. And the advantage, of course, in doing that is they got much more contact between the fractures and the rock compared to the vertical or slightly deviated wells in Sulz, where they produced only a small number of fractures. So this is an attempt to actually get to that surface volume ratio that I talked about before. So Fervo did their first project in a place called Blue Mountain in Nevada. They called it Project Red, and they drilled what are effectively the first horizontal wells in geothermal. It wasn't necessarily given that that could be done very easily, because we're talking about very different kinds of rocks in geothermal than we have in oil and gas. So, shale plays are typically sedimentary rocks, which are relatively easy to drill, but geothermal formations are typically volcanic. They're very hard abrasive rocks and much more challenging to drill. So this was an adoption of an oil and gas technique, but it wasn't a straightforward application. They actually had to modify the way that they did things. But you can see what they did here in Project Red in Nevada. They drilled these 2 wells in 2022 and then fractured between them. So this plug and perf stimulation, common in oil and gas, was the first time it was applied in geothermal. It was successful. So you can see here on the left is the plan view, on the left is the side view. And they did 16 stages of perforation in the injection well and 20 stages in the production well. And this is the microseismic cloud that you see that was a result of doing that. Blue are the injection well treatments and red are the production wells. Well, one of each. The vertical well that you see here was an observation well so that they could actually see what had happened. And this is a very important diagram. This actually shows that it's a production log of the horizontal section of the well and the 16 stages on the injector, looking at the flow rates into that injector. And what you can see importantly is that they were actually flowing into most or all of the stages. So this is an important point, is that these 16 stages of stimulated fractures cover a range of about 2,000 feet. So actually this distributes the flow over a very large volume of rock. So that well pair in Project Red was put into production in October 2023, just about 1 year ago, and they are producing electricity in the Blue Mountain plant and selling it actually to Google. So that was their kind of first trial. Fervo then moved on to a full-scale project in a place called Project Cape, which is in southern Utah. And they are now drilling, they're batch drilling their horizontal wells. They've drilled, so far they've drilled 15 of them. And this is going to be a much larger project, ultimately reaching 400 megawatts. And I draw your attention to the fact that the other projects I talked about in Europe, it's in Australia, etc., they were 1 or 2, 3 megawatts, something like that. So Fervo is for the first time actually developing EGS at scale, and you can see how they're laying out their pads here in Utah. Interestingly enough, here on the right side of the diagram is Utah Forge. That's the DOE research project. They also have drilled wells not quite horizontal, they're drilled at 65 degrees. And this is a stimulation that Fervo did this summer in July. They now lengthened the horizontal well section to 2,500 feet, and they're putting in 27 stages, plug and perf, along that length. And in the end of July, they actually did a circulation test between their first well pair, and they were able to flow, you can see the red one up here, maximum of 120 kilograms per second, stabilizing at around 90 kilograms per second. And because they have a downhole temperature of 195 degrees centigrade, that would represent about 10 megawatts of electricity production in their first well pair. And they're ultimately going to drill many. So if we look in side view, interestingly in this diagram, you can see there are actually 3 geothermal projects. Fervo on the left, Forge in the middle. You can see their 65-degree wells. And on the right-hand side is a conventional geothermal project called Blundell, which has been producing since early 1980s. That has no stimulation and the wells are all vertical. So this large pink body is a sort of granitic crystalline rock in which all of these systems are developed. The Blundell plant on the right is convective, so it has faults and fractures that bring the geothermal fluid much higher to the temperature, higher to the surface. You can see the temperature contours here, whereas Fervo and Forge are in a conductive part of the surface formations, which are actually widespread across pretty much everywhere. And if we look at that same, the Fervo wells in sort of gun barrel view, this is looking along the horizontals, you can see they're developed in paths, 4 on the left and 8 on the right. And you can also see the 3-dimensionality of the configuration. They're not just laid out horizontally, but they also have flow in a vertical direction. Now, some of the innovation that Fervo has done actually is associated with drilling. So I want to talk about that. It's one of the most important things that's been happening. One of the problems with geothermal drilling is that it's difficult because the rocks are very hard, and because they're typically drilling in fractured formations, they want the fractures for the large flow, they get problems with lost circulation and things like that. So shown here are the days versus depth drilling of conventional geothermal wells in Blue Mountain in Nevada. So there's an existing geothermal field there. And you can see that some of these wells take, 60 days to drill, even to relatively modest depth. And that, of course, translates to a large expense. The first two wells that Fervo drilled in Project Red, actually on the side of Blue Mountain, also took about 60 days, although they drilled to much greater measured depth because of the horizontal section. But importantly, what you can see is that over time, between the three wells, this is the vertical one they did first, they were beginning to improve their drilling rate. And then if we go over to Project Cape in Utah, they then went into sort of a batch drilling mode where they're drilling the wells all on the same pad with a rig that can be easily skidded over to move to the next one. And what you can see is now they've managed to reduce their drilling time to much greater measured depth, including the horizontal section, of around 21 days, which is actually spectacular from a comparison with conventional geothermal drilling. And if we look at the learning curve that they've experienced in the wells they drilled at the time that this diagram was drawn, they had anticipated that they would be able to shorten the drilling time, but their actual observation or the actual experiences, they reduced it much more than they had expected. Okay, and the way they did that was by a number of different techniques, but one of them was the usage of PDC bits. Interestingly enough, PDC bits are used commonly in oil and gas, but they were originally developed for that Fenton Hill project I mentioned back in the 1970s for Fenton Hill, EGS. So Fervo experimented a lot with PDC bits, which have not previously been used widely in geothermal other than in Fenton Hill. One of the things that they found is they were able to put a lot more weight on bit than was typically the case with roller cones, which had normally been used before. They don't weight up on those bits so much in the hard rocks because they break the cones and they get too many trips. But using PDC bits with more weight on bit, Fervo and also Forge as well, actually, were able to get much longer bit runs, and that enabled them to drill faster and with fewer trips. Now, if we take a look at the consequence of that, again, this is my student, Mohammed Al-Jubran, PhD student at Stanford. As part of his research project, he was looking at the cost of developing EGS projects nationwide, or here in the lower 48, in terms of the ultimate cost of electricity, LCOE, levelized cost of electricity. So although we can develop EGS pretty much everywhere, it isn't, of course, economic everywhere because you would have to drill too deep to get the temperatures that you want. So Mohammed did this very careful study evaluating the levelized cost of electricity, and you can see it varies a lot. It's most a function of the temperature, but not only that. And for comparison purposes, you look at the scale on the right-hand side here. The average price, levelized cost of electricity in the United States is about $75 per megawatt hour, somewhere around here, the transition between red and orange. So what you can see here is that although you could develop EGS pretty much everywhere in the lower 48, in most of the places it would be too expensive to be economic. But if we look for the oranges and the reds, there are places that are attractive for EGS right now. This calculation that's shown on this map, however, is based upon the drilling rates of 2022. That was before Forge and Fervo actually made the advances I just talked about. So if we do the same calculation based upon Fervo's and Forge experience with 2024 drilling rates, this is what the EGS map looks like in terms of LCOE. So again, we're looking at this is a shortened scale. Now, the yellow, the straw-colored yellow would be comparative economic price, $70 per megawatt hour. And you can see that most, although not all, most of the United States is actually accessible at that temperature. And these red zones actually are accessible at much lower temperature, $30 to $40 per megawatt hour, which is competitive with wind. So to summarize then, all of those four issues that I talked about actually have been overcome in the Fervo and Forge projects. And added to that is an improved drilling rate, which actually has significantly lowered the potential cost. Now, I want to move on and talk about scalability because, you know, we need to do this more than once. So again, calculated by Mohammed Al-Jabran, looking at the range of the supply curve as a range of price, compares the LCOE for geothermal compared to other sources like wind, solar. Conventional geothermal is this bar up here, which is around $70 per megawatt hour, solar plus battery and biomass. So these different curves show if you drill to various depths between 1 and 7 kilometers, and the red line on the right is if you don't care about, you drill to whatever is the optimal depth. And what you can see is that the amount of energy which would be available under these different prices is quite a lot. So for comparison, you can see this scale is in gigawatts. The electric production of the United States right now is about 1 terawatt, which is 1,000 gigawatts. So basically that amount of electricity would be available at a cost of $40 per megawatt hour if we wanted to do that amount of geothermal. That isn't what anybody is proposing, but it means that it's possible to have a significant fraction of geothermal energy in our nationwide portfolio of electricity. If we look at the capital costs, geothermal is more expensive in terms of the original capital outlay, but again, competitive with many other sources. And earlier this year, the Department of Energy did this so-called liftoff report, looking at how we can make geothermal energy economically attractive. And what you can see is, you know, in 2021, this is looking specifically at EGS. This diagram is a bit confusing because it shows both capital costs, which are these green bars here, as well as the LCOE cost, which are shown here in the boxes. So the capital cost in terms of dollars per megawatt installed was 28,000 in 2021. That was the original. And then what you can see here, the reductions due to the aspects I just talked about, like the drilling cost, for example. So although it's not named in the DOE report, this is basically Project Red, the one I showed you in Nevada. So that cuts the cost almost in half. And then you can see these other reductions due to other innovations that have been talked about and actually also experienced in some of those projects. So this so-called liftoff target here actually is more or less where Fervo expects to be in Project Cape, because of the fact that they are drilling multiple, 8 wells per pad. They are planning to use a standardized power plant and put 1 power plant per pad, which actually saves the cost of the gathering system, the pipelines, which is a normal part of a geothermal operation. Sometimes the wells are 2 kilometers away from the power plant. So in a typical development, the gathering system, the pipeline system, is about 20% of the cost, and that's basically removed if we put a standardized plant more or less at the wellhead of that 8-well system. And then this is DOE's so-called Earthshot they're looking for further reduction by 2035. But what you can see is this figure right here, we're more or less there with Fervo's Cape project. So in conclusion, over the last 20 years or so, there's been a widespread development of geothermal worldwide, largely conventional systems. But EGS has been expanded and advanced by those innovations I mentioned. And most importantly, the drilling cost reduction really opens the door for EGS in many other places. The remaining issue that I'm not going to talk about today in detail is matching geothermal into a grid which has a lot of variable power, like wind and solar. Because EGS power plants like to run at 100% load all of the time, 24/7, so-called base load, which used to be a good thing. It is actually now more challenging because of the strong variation in the load or the generation during the day from wind and solar. How do we fit in a base load source into that mix? And that's something that people are working on right now. So with that, I will conclude and thank you for your attention and invite
Thank
your
you so
questions.
much, Dr. Horne, for this informative session and for your effort and time as well. For a quick Q&A session, the first question, what types of wells are mostly used for geothermal production?
What kinds of wells?
Yeah.
Well, they're kind of regular wells. The ones in Fervo and Forge are unusual for geothermal. So conventional geothermal wells are typically drilled with open hole completions over thousands of feet because they want to get all of that contact. Commonly, they use slotted liners in case of well collapse. So they are otherwise kind of normal wells. The EGS wells I talked about for Forge and Fervo are plug and perfs more or less on the same configuration as we see in shale oil and shale gas. The principal difference is that the diameters are much larger. So I remember that we've got to produce 50,000 barrels a day. So typically the casing size for those systems like Fervo 7-inch rather than 5-inch is what we would normally see in shale oil or shale gas.
Okay, thank you. How do you see the role of geothermal energy evolving within the global energy mix?
As I showed earlier, you see that some places have really a lot of geothermal energy, and that's very advantageous for them. Here in the western states, California and Nevada enjoy geothermal energy a lot. And the possibility opened by EGS is that basically you could have that kind of contribution from geothermal more or less anywhere in the United States, not quite anywhere, but even on eastern states, we could have geothermal, and that would be very useful for displacing fossil fuels, as well as filling in the gaps which are left if you have a strongly intermittent system with a lot of wind and solar energy. So I don't know exactly where this could go. In Kenya, it went all the way to 45%, but it's not unreasonable to imagine that geothermal could produce 10% of the electricity for the whole United States, just like it does in Nevada now.
Okay, thank you so much. And the last question, what specific regions of the world have the most untapped potential for GES, and how can these areas benefit from increasing geothermal development?
Yeah, so the places that are most advantageous for geothermal right now are places which are kind of volcanically active. So the so-called ring of fire around the Pacific. If you look at those countries that are producing geothermal energy today, There are California, New Zealand, Hawaii, Indonesia, Philippines, Japan, all around the ring of the Pacific, as well as Iceland, Italy, has the famous volcanoes, Vesuvius, etc. And then the East African Rift Zone, all of them sort of tectonically and volcanically active. So they are hot places. However, EGS gives the potential to produce geothermal energy in not so volcanically active places. So I showed you the examples in Europe, and the European countries are strongly interested in EGS. There's been projects in France and Britain and Germany and Switzerland, actually operating plants in France, Germany, and Britain. They just started one up in Britain recently, and Switzerland is developing a new one too. So Europe is highly attracted to EGS, as is the United States. Japan is another place that would be very attractive for EGS because they have both conventional and EGS possibilities throughout their islands. So in principle, EGS could be done almost anywhere. So places that have expensive electricity would be the places to go for first, but there's relatively little limit to where you could do it.
Thank you so much, Dr. Horne, again. And thank you all for attending. Highlighting this session is recorded and will be uploaded soon on Patreon YouTube channel. So make sure to subscribe in our YouTube channel. Waiting for you in the next session. Thank you all. Bye.
Bye-bye.
Bye.
Thank you very much.
Professor Horne, this is Mohammed Solomon. Thank you so much for accepting our invitation and coming to this presentation.
Very good.
This was great. Thanks a lot.
All right. See you again.